Hope you're all fine. Getting started earlier than usual with all technical delays the last lectures. Starting a new subject, not a new mega subject, but new subject. Talk about the definite integral. Yes, the one we use in high school to calculate areas between the graph functions and the x-axis. And we're going to define it mathematically, gently, and it's gonna take some time, not all the lecture, but after we define it, we can prove some simple statements about it. The our work is kind of parallel to what you have done last course with errors when it comes to the definition of a derivative. I mean, I don't know how exactly errors showed it, but we start with a pure geometric notion. The slope of the tangent line to the graph of the function at some point A. We want to define uh, that geometric notion mathematically, and we finally, eventually, we get the derivative, the limit fx minus fa, etc., etc. So when it comes to integral, we would like to do the same. What is the geometric notion we're trying to define? It is what is called the assigned area, meaning the area beneath the x-axis and above the graph of the function is considered negative, and they can cancel each other. Let's write down in one sentence. We want to define the signed area of a function in a segment column AB, possibly Hebrew. The sign the area above the x-axis beneath the graph is considered positive, and area beneath the x-axis and above the graph is considered positive, negative. For example, we denote if such area exists, we denote it with integral from A to B, fx dx. It is called the definite integral. Said with bold for definition for the notion itself. Definite integral of f in AB, along AB, above AB, whatever. As in derivatives, nobody assures us that such an area actually exists. And we'll see in examples even today. First of all, one could think of unbounded function, goes straight to infinity. It's just logical. It doesn't have any area between it, or an infinite area between the graph and the x-axis. And we'll talk about such infinite integrals something like lecture 8, lecture 7. We'll see how we go. We'll see some uglier examples, functions that are bounded, but eventually do not have the notion of area is not defined for them. The notation here is a bit tricky because we all know, let's write it down with a different color. Sure. Preferable color, someone?
For what?
Just color. Just choose a color. Something.
Red.
Red. No, that's a good one. It's not, you don't see it well on the white background of the PDF. Let's just choose blue. We all know, kind of big spoiler. The integral. I mean, we all know the formula. Integral a from b, fx dx is big F at b minus big F at a, where f is an antiderivative. And we'll get to this statement, this sentence, but only in lecture 6 next week. B'ezrat Hashem. Now, one must remember that the indefinite integral, finding the antiderivative, and the definite integral, what we're going to define now, the area between the signed area between the graph and the x-axis, are completely different. The connection between them is actually a wonder. What the derivative, the area, why should it be connected? We'll see it, as I said, but only in lecture number 6. Now we have, first of all, our mission, and as I said, it won't be very easy, not very hard, but not very easy on the other side. On the other hand, to define this definite integral, to define the signed area. So let's say I have a tabula rasa, that's for the Latin, and paint a little. Let's say we have a graph of function and a segment AB. I'll draw it above the x-axis, but it's not, as it was mentioned, necessarily so. Could be under, it's all good. And the function graph, let's put A here and B here, and I have our function. Let's make it a little bit steeper. We want to define, or maybe one can say define a good way to calculate this black area between the graph and the axis. How can we do it? Any ideas?
Wait, I mean, we can do an approximation
With?
and doing like bars, and we have like the area of the bars.
Okay.
Right?
Sounds like a good idea. We can approximate the area using a geometric shape. We can easily calculate its area, such as rectangles, bars, as you said, and using some kind of limit, which kind, well, we're going to see, getting closer and closer to the real area. And the definition will be, okay, let's take this limit of such areas of such bars. If this is the signed area of the function here in this segment. As the derivative is the limit of fx minus fa, etc., etc. So, how do we build such rectangles, such bars? First of all, I'll write it down shortly. We can choose some points along the segment. Let's call them x1, x2, x3. They define the bases of the rectangles. Secondly, we need to choose, let's have another color effective. Choose some points in the subsegments. Each point will give us the height of the rectangle. Of course, the height should be a point on the graph itself, not on the ground. And when we have both points of the bases and the points of the heights, we can draw our rectangles. I'm drawing it with my fingers, so it's probably not the most accurate rectangles you've ever seen, but you forgive me. Okay. So, first of all, is the right first step to do. Approximate the area using rectangles. One can easily see that it's not the actual area. We have some gaps for the function, and on the other hand, for the rectangles. Sometimes they are above the function, sometimes it's vice versa. So it's only our first step in the definition of the signed area, but it's a good first step. Let's don't think you can see it on the screen. I take a picture of the screenshotting, yeah, the drawing, and then I delete it and pasting it back as a PNG. Advanced technology. Now, let's say 16 width and I don't know, man. Say 8. Thanks. So, first of all, we look at a partition of the segment AB. Let's define more formally what the partition actually is. A partition, let's say use the letter P, partition of the segment AB. Come again?
Where does that go?
To define the area.
Define that.
Yeah, what actually is define the area or define a way to calculate, because one can say, well, I can see it, it's here, the area between the graphs. But I consider it defining the area itself, the signed area itself. AB is a set x0, x1, etc. It's right points that you actually see till xn, where xf is actually the left side of the segment, which is smaller than x1, which is smaller than x2, and so on. And xn is the biggest point. Partition, it's actually the right side of the segment. So these are points. First of all, for the partition. Secondly, we choose a point CI in every subsegment, let's call it that way, between x minus 1 and xi. The set of denoted with C, because we're choosing points. Set of C1 to Cn is called, I don't know, choosing. In Hebrew, I call it point choosing. בחירת נקודות. Probably the better name. First of all, we have partition, and then we have point choosing. See? Now we can look at the rectangle with bases. Bases or base? Whatever. The bases xi minus 1 xi, and the height, I see right it. No?
EI.
EI, all right. FCI. The rectangles, so plural. Their combined area is an approximation to the real area. Real, because we are actually trying to define it right now. But intuitively, we can look at the picture and say, okay, this area here, right there. This combined area is called the Riemann. I think that is to write his name. Let's Bernard Riemann. Huh? Like that? Yeah. Sure. Let's check it. Bernard. My God, for a second. No. Yeah. But you have age in his first name. It's Bernhard or something like that. Kraut.
Can I make it full screen?
Yeah. Yeah. Riemann sum of F with partition for partition P and point choosing C. We denote it with some, I don't know, S, like some R because Riemann, and let's say F, P, and C. It is actually the sum I running from 1 to n. Area of rectangle, base and height. So FCI is the height, and xi minus xi minus 1 is the length of the base. And this area, yet again, is an approximation of the real area. This is our first step, having an approximation. Now the next step should be operating some limit in order to define the real. Is it better?
The real.
The actual area between the graph and the axis.
So F is found rectangle.
Here is the rectangles with a specific partition P, a specific point choosing C.
Would that be the same thing writing?
Huh?
Would that be the same thing writing in different?
Yeah, it's called huh?
I'd say rectangle
Malben.
would be S now.
No, the R is for the Riemann.
Uh,
I'm teaching it Hebrew, I still write SR. So now the question is how do we step up our game? How do we actually getting closer and closer to the, again, real area? So looking back at our good Rembrandt, yeah, photo drawing, how can we have a better approximation of the area? Yeah, we can choose adding, we can add point to the partition before adding points to the point choosing and having a better approximation. I agree, but we have to be more precise. Let's say, for example, we are adding a point here, a red one. So by adding a point and then considering two rectangles instead of one, looking just at this subsegment, we can easily see that there is an improvement. Yeah, the gap between the rectangles and the function is now smaller than it was. Can have Control Z, you can watch it, then Control Y. The gap is just this and this instead of all this, I don't know, pizza slice. So intuitively, it is correct. Adding points to the partition and so to the point choosing improves the approximation. But we have to do it wisely. Meaning that if one, for example, adds a lot of points to the partition, but only in this subsegment, and only here, we'll have a great approximation. You can show to your parents, they'll be very enthusiastic. But what about our other subsegments with their big gaps, the big gaps in the resumes? How can we solve it? How can we explain them? It's not the NDA. How do you call it? I know you nothing. So we want to add points to the partitions, correct? But we have to add them in such way that every segment becomes smaller and smaller. Now, if we want every segment to become smaller, and actually the length tending to zero, we can say, using the sandwich rule, we are adding points in a way such that the emphasis I don't know, is it? In a way that the biggest segment tends to zero, becomes smaller and smaller. And if the biggest one becomes smaller and smaller, of course, all the rest of them are becoming smaller too. So this is our next step. Let's delete it if you want, or having another photo if you want. Quickly. Winky Shift S. Never knew I would use it so much. This keyboard shortcut. But life can be surprising sometimes. I need to save the file itself for the computer start to explode or something. Okay, now let's save. Can have a glimpse of my Dropbox. It's very well organized. It's a new bro, nonetheless. MP2. Here is the shadow. And MP2. 4. Okay, so now adding points to the partition gives us a better approximation. That is correct. But we need to add the points wisely in order to get closer and closer to the real area. As I mentioned, having the biggest segment tending to zero. So we denote by lambda of p the length of the largest subsegment P is actually maximum of between x1 minus x0, x2 minus x1, so on and so on, xn minus x minus 1. And lambda is called the parameter of the partition P.
After
Yes. I don't know if it gets you confused, but native Hebrew speakers keep the letter Gimel. It looks like just like the letter Gimel. So every student is, Elad, what about gamma? And every time it's not gamma, it's lambda. Gamma, you have the little one who looks like dead fish. This, I mean, I don't know. The sound that I think of it, it's not something like dead fishes I'm looking right now. And you have the big one, which is like I don't say it in English, where you hang the people, execute them. Mu?
the small u.
That's mu.
And then you gamma again. It's y. Okay.
That's gamma mu. How do big mu? Do I have big mu here? I don't. Lambda is called the parameter of, okay. So what we actually want to look at is the limit of the Riemann sums of the areas of the rectangles where lambda p tends to 0. The
So
yes.
when they get distance between two points is 0, so it's fully under the curve. So gamma p is the biggest distance between 2 points we select x
Yes.
I and xi plus 1.
Mm-hmm.
So we want to see the area when the biggest one is 0, meaning
Yes, to 0
under the curve. So like all of the bars are under the curve. That's what we're trying to see. Right?
No, there could be a above them. I mean, but the bars themselves are getting thinner and thinner. All of them. Let's have an example for gamma, then write the main definition. For example, for let's say p is 0, half. You see the fractions? 2/3 and 1. Partition of the segment 0 and 1. We have lambda p is, what is the largest, the greatest? It's half, right? We have 3 subsegments between 0 and half, half and 2/3, 2/3 and 1. The biggest one is 1, 0 and half with a length of half. So now, what is the signed area? Signed area of the function f in the segment AB defined as follows. If the limit where parameter p tends to 0 of our Riemann sum Control C, Control V. exists and is the same for every partition P and for every point choosing C, then the area, which we already denoted with the definite integral, is that limit. Now it's very, one can say, complex limit comparing to what we are used to from the first course of Infi. In the first course of Infi, you discussed limits of functions from R to R, meaning one real variable. Here, let's say f is constant, is the same function with every partition, but here it's a function of two variables, p and c. For every p and c you put in, you get a different combined area of the rectangle, a different Riemann sum. And p and c are not real variables. They are both sets of real variables with changing number of elements. So it's a very complicated limit to calculate. We'll use the definition for very simple examples today. A constant function and the Dirichlet function. If you know it, if you know, if not, we're going to see. You're gonna have a lot of fun. But very quickly, we'll move to propositions, statements, theorems about the integral, and we'll use those propositions, theorems, etc., in order to calculate integrals and not the definition, which is very ugly. Yet again, we've already spoilered the spoiler. We all know from high school, using the big F, the n-derivative, calculating the area. But as I said, we have this lecture and next lecture, and only in lecture 6, we can see the exact formulating of this theorem, connecting between the definite integral and the derivative.
I remember seeing somewhere that it discussed that sites using bars on the height. That's another technique of doing it by like longitude, like by longitude instead of like vertically, and like that's better in some cases. Do you know what I'm talking about?
Yes, it's called let me write down another sentence and then I'll answer the question. If the limit exists, the function f is called integrable. No, it should be bold, not m. Integrable. And now for your question. Here at calculus, and most of the students that already see it's enough, we define what is called a Riemann integrable function. There is a different method, different approach in defining integrals. It's called the Darboux method. It's another dead French guy. I mentioned him in our first lecture. And Darboux says, you know what? You don't just take a random point Ci in every subsegment. You take the supremum of f and the infimum of f in every subsegment. You get two kinds of rectangles. One is always beneath the graph, the others are always above. And if those sums kiss each other when you take lambda and draw it to 0, then the function is integral. Riemann and Darboux actually say the same. One can prove that they are equivalent. We're not going to do it here in our course. We define the integral with Riemann. It's more than enough. Now, what you say about taking the longitudes It's different, another equivalent way of defining integrals is called the Lebesgue integrability, another French dude, which is already dead. And there are Lebesgue integrable functions which are not Riemann integrable functions, and not vice versa. Every Riemann integrable function is Lebesgue integrable function. And there are different approaches, methods to define integral. Stiltius, he's not French, but he's dead. And other people name. And here, when it comes to basic calculus, I know it's in Fit 2, but still, it's a basic one. The Riemann slash Darboux, and yet again, we are focusing on the Riemann approach when it comes to integrability, is what we're going to discuss. I mean, the Lebesgue, it exists, and it's important mathematically, but as far as I can tell, at least in let's say in your first degree in the BA or BSc, whatever it's called, if you're not a mathematician, you're not going to discuss it. Only the Riemann slash Darboux way. As I said, it's complicated. It's much worse than the definition of the derivative. Yet somehow, we think of derivative and integral as two sides, the yin and yang of calculus. But what was true for the indefinite integral for finding the derivatives is true here as well. It is much harder, it's much more difficult to calculate integrals when it comes to definite integral as well. Yeah.
Can you give an example of
Yes, I want to give you two examples.
a function that isn't integrable?
Yeah, I want to give an example for such function, but I want to do three things. Three things before that. First of all, I want to write down a bit more convenient way to look at this limit. Secondly, I want to give an example of a function that does have an integral, and how do we calculate it from the ugly definition, and then we can move forward to a function which is not integrable. And I said three things, not just two. And the third thing is that it's clear from the definition, but it's not. I didn't write it explicitly, so I want to write it down explicitly. Note, we discuss, no, much used, discuss integrability of bounded functions only. Unbounded functions. So lecture 8, maybe even 7. Let's see how we roll. If the heights of the rectangles are higher and higher and higher and tends to infinity, or to minus infinity, the same, it's clear that the area is not defined. But one can say, hey, after we finish 2 weeks, very enjoyable weeks, talking about Riemann integrals, one can say, oh, we know we talked about sequences and series, and we can somehow tame the infinite. But lecture 8, let's not talk about the future in the present. Yeah.
Just scroll up a bit.
Yeah.
The name of the item.
He was German. He is dead, though. They're all dead.
Did anyone who studied you isn't dead?
I don't think so, but in our last chapter of the course, talking about functions of more than one variable, we'll see a theorem from the 20th century.
Wow.
Yes, brand new when it comes to calculus. When it comes to computer science, many of the people are still alive.
That makes sense.
Yes. but math is Asian. We all did long time ago. So first of all, we know we're discussing with the boundary function only, and boundary functions lecture 8 or something like that. And now, probably you studied infinity with errors, and errors likes this approach very much. So do I, and I learned it from him. Defining limits and everything around them using sequences. I mean, defining the limit of a function, not using epsilon and delta. Maybe showed you the Cauchy way to do things, but the Heine way, function limit of the function is L. If every sequence you put in goes to L as well, Errors uses it much more, and so do I. So to make it a bit easier, not easy, but a bit easier, we can look at this limit using sequences. Meaning, we can look at the limit from the definition using sequences. The function f is integrable, meaning it does have a signed area, which we denote with this nice integral AB, etc. Is integrable if for every sequence of partitions, let's call it PM. I use M as index because N is used for the points inside every partition. It's not very important, but this is why I changed the letter. Partitions PM, it was like this at first place. PM with parameter that tends to 0 and for every sequence CM of point choosings sounds weird, but don't know. Where's the H? We have the same limit. Now when it's defined with sequences, one can say, okay, let's take M to infinity. Always happens in sequences and PM and CM. So let's have a very simple example. Example, we look at a constant function fx, we will then fx is c for every x in our segment AB. Intuitively, the area is very easy to calculate. Let's draw it quickly. But hopefully, one straight line. Color with some purple. Then we have, here it is A, here it is B. And this is the function f, which is always c. Tell me, dear students, what is the area?
I wonder.
Yes, it's a rectangle. The height multiplied by the length of the base. C, B minus A. This is what we are expecting to achieve from our wonderful, horrifying formula.
We managed to finish calculus into very much.
Oh, we got calculus 2, the revenge of the integrals, or something like that.
Okay. Right back.
Yes. If you want a new hope, if you do, 16, let's say 7. So we expect to get C and B minus A. If we succeed, we're not physicians, we're not chemists. It doesn't mean that our definition is good. One succession means nothing in one trial, but on the other hand, this is definition. Don't expect anything. So, let's calculate the area. Another way we actually see that it does exists. The way we do so is with the sequences. I mean, we have let M be a sequence. Where's the sequence? No. Of partitions such that the parameter is going to 0 when M tends to infinity, and let Cm be a sequence of point choosing. Just let it be clear, the sequence of this point choosings is what is the word I'm looking for? Corresponding to the sequence of the partitions, meaning every point Ci is in the subsegment xi minus 1 xi, not some different subset, different subsegment. Let's write down the Riemann sum is where is it? Oh, it. The sum is going from 1 to n. As I mentioned, m is the index of the placing of the partition in the sequence of partitions. And n is the number of elements in every partition. Let's say, for example, we looked at the fs 0, half, 2/3, and 1 partition. This can be partition 1. And when you add, I don't know, the point quarter, then it is partition 2, etc., etc. Now, partition 2 has 5 points, not just 1 or 2. So it's different indexes. One is the number of elements in the partition. This is n. And one is the place of the partition in the partition sequence. So this is the Riemann sum. Very nice, very elegant. F is constant. It is C. Always C. So we can write down C instead of F to Ci. And C as a constant can be plugged out from the sum. And we get C on the sum of xi minus 1. Now this sum is constant as well. And why is that? First of all, one can think of it, what are we actually summing here? the length of the subsegments. If you sum the length of the subsegments, you actually get the length of what?
The segment.
The segment itself, which is b minus a. Very good. Another way of thinking about it is writing it down explicitly, and it becomes what we used to call a telescope sum. That's what we call it in Phi1. Telescope. When most of the elements cancel each other. I mean, you have x1 minus x0 plus x2 minus x1, and so on and so on. Xn minus 1. And most of the elements cancel each other. And we are left with xn minus xfs, which, as we mentioned before, in our notation are just b and a, the site the element of the segment, and as we expected, using our definition with this very simple example, a constant function, was probably the most simple example ever, we do get what we expected to do, C, B minus A. Now, after you finish writing it down and maybe have questions, we can look at a counterexample, function that is not integrable. So, in conclusion, f is integrable, and the integral, the area, the signed area between f and the axis is C, B minus A. So, I want to emphasize it. It's two not different things, but let's say two levels. I mean, first of all, f is integrable, and then it's not just integrable, we can say what the integral is. Now, most of the time we do both of the things in one shot. And when it comes to derivatives in the first course, that's what happened as well. I mean, most of the times when we wanted to show that a specific function is differentiable, we actually calculate derivative. Not just saying it has derivative. It has derivative, and derivative is blah, blah, blah. But on the other hand, we know that sometimes one could say, yes, the function is derivative without actually calculating the derivative itself, the differentiable, without actually calculating the derivative itself. And when it comes to integrals, we'll see this gap sometimes as well. One could say, yeah, the function is integral because of this theorem or because of this proposition, but calculating the integral is something else. Here, the difference is very tiny, function integrable, but we actually see what the integral is without any separation. Any question about this example? Yeah.
No, yeah, I'm just wondering if this is the proof for this specific example when the function is constant.
I didn't understand what you said.
You say in conclusion, f is integral.
Yes, in this specific example, of course. Yes.
What did you say big C was?
Big C is just a constant.
But we're saying we don't know what f of ui is.
But we know that, yes, it's the same C for every Ci, for every Xi, for every point in our segment. Yes, the function is constant.
Oh, right. Yeah.
Yeah.
Like that.
Now, let's just say I'm not going to do it, maybe probably near in practice, or not. As a big boy, as I said, besides. But if the function was very simple, not that simple, let's say fx is x, it will be a whole different story. I mean, instead of fci, I can write down, okay, ci. Now what? So, for every point choosing, you get different ci's, and it seems to be very complicated to do such calculations using the definition, as I mentioned. Very simple example. One good example, the function is integrable, coming right up. And counter example, when the function is not integrable. And then we'll start. I mean, time is running when you are enjoying, you're saying, here, bro. Almost an hour passed already. We'll start formulating theorems, propositions, etc., that will make our integrable life easier. Now, for a counter example. Example, let f be the Dirich, I think it's you write it that way.
Dirichlet.
Let's let's Dirichlet. I don't think it was a French, surprisingly. No, it's without the I, without the Peter Gustav Lejeune. Okay, it was
It was
half
in
French,
French.
half French or something. Wikipedia says he was German mathematician, but where's the Lejeune? Why Lejeune? Um, Oh, he was born in Diorén or something like that, a town on the left bank of the Rhine, which at the time was part of the First French Empire. Reverting to Prussia after the First Congress of Vienna. Wikipedia is one big rabbit hole. Stop it now. Huh? Yes, sometimes on purpose, which is worse. I don't know how much you're familiar with Israeli sports, especially when it comes to soccer or football. Um, I had a friend who was a big fan, ultras of Beitar Yerushalayim, if you know. It's called La Familia. They're very racist, very good. It was a good friend of mine when we were in high school. And I mean, one time the one game was actually stopped because they broke into the field, and the photo next day in the newspaper of the sports newspaper, it was actually him. He was holding his scarf. I know you say it with the La Familia written on it in the middle of the field. So he used to enter Hapoel Tel Aviv Wikipedia page from time to time, every time from a different IP, and editing some of the paragraphs with, let's say, profanities. Okay, about Hapoel Tel Aviv, and every time he was blocked, opening a new user. So that was fun times 20 years ago, something like this. Yeah, 25, 26. Um, yeah, now the bots are much harder to go through, but yet again, some of the information is not totally correct. Put it that way. Okay, let the reflect function, which is defined that way, is the indicator function of the rationals, meaning it's one for every rational number q and 0 when x is not rational. Let's say, I don't know, in 1 to 0, 0, something like that. Now, the limit should be the same for every sequence of partitions and every sequence of point choosing. Rationals, without using big math words, doesn't matter how small the segment you look at is, you have a rationale there. So we can look at two different kinds of point choosings. Now, let's PM be a sequence of partitions On one hand, we can look at a sequence CM of point choosing with only rational numbers in every CM. So having the Riemann sum to be always 1 when it comes to FCI. And as we mentioned before, the sum of the length of all the subsegments is just B minus A with specific, I wrote it 1 to 0, but can be A, B, and general A and B nonetheless. So let's write A, B. You can state 1, 0, whatever. It's 1 minus 0, which is 1. Get it nice and clean in one line. On the other hand, looking at CM different sequence of point choosing with only irrational numbers, we get the Riemann function, the Riemann sum is 0 multiplied by whatever, which is, of course, 0. So for one kind of point choosing, it is always 1. For another kind of point choosing, it is always 0. You take m to infinity, be my guest. It's always 1, 1, 1, 1, 1, 1, 1. And on the other hand, it's always 0, 0, 0, 0, 0. It is not the same limit. It's not the same limit. So we do not get the same limit for every Pn and every Cn, meaning the function f is not severable. Even though, see, right?
Yeah.
It is bounded.
I don't think it matters, but you wrote integral less networkable, but
In what? Integrable. Yeah. When I write Hebrew, I always always confused as well. The most common one is Ingertal. Yeah. You're going through my PDFs in Hebrew. You Control F Ingertal. Many results. Write down quickly, or as quickly as I can. And I misplace some letters here and there. So we can see we have a counterexample for a function which is bounded but is not integrable, but is an ugly one. Just like integrals, the indefinite integrals, it is. I like to put it that way. It is harder to calculate an integral than it is to calculate derivative, because much more functions have an antiderivative or are integrable instead comparing to differentiable function. Many functions are not differentiable. If it is not continuous, it's not differentiable, and when it has some points of, we'll say, spitz, Yeah, like absolute value is 0, etc., etc. All such functions will have a theorem Tuesday, coming up next Tuesday. Every continuous function is integral, and there are many integral functions which are not continuous. On the other hand, not every continuous function is differentiable. So being differentiable is much more, say, exclusive.
Okay.
No. On the contrary, I mean, every differentiable function is continuous and so is integrable, but there are many, many integral functions which are not continuous and of course are not differentiable. So being differentiable is much more exclusive. So it's, if you think about it, it's not very surprising that it is easier technically to calculate derivatives, because all the functions we are discussing when we calculate derivatives are very nice ones. They're the best students in the faculty. It's not the one who are almost, not the ugly one. Not the, let's say the liquid, not the delinquent students who were smoking outside the class. Any questions? So just a little notation, and then we can move forward. As I said, starting the theorem, propositions, etc. Notation. We denote. We actually are not going to do it so many, but let's write it. Okay. We denote the difference xi minus xi minus 1 with no, not lambda. I want it's big lambda. It's big lambda. No. How do I write the triangle? I just forgot.
Delta.
Delta, right. Made the Greeks burn in hell. Delta. I do have a triangle here, but it's a bit different. Irritating way. Pheno somehow. I don't like it. So it's delta. But one can write xi minus xi minus 1. It's completely fine. That's what we did in the past, in the last hour. Okay, that's our notation. Any questions? Something before we move on? Okay, so in order to prove or at least state our next propositions, I want to show you a different approach, of course, equivalent one, but a different approach to define the integrals, not the Darboux versus Riemann that I mentioned before, but some different method. Now, I call the mathematical notation tnuda in Hebrew. And I don't know exactly how to translate it to English. Let's ask Mr. Google. Tnuda. Such like the right? Oscillation. That's a good one. Oscillation. Okay. Let's have a headline. Of course, oscillations. Let f be a bounded function in AB. Let's make it clear. All the functions that we're discussing here are bounded. Even if I'm not mentioning it, they are bounded. As I mentioned, we'll go to lecture 8, Bezrat Hashem, then we talk about unbounded functions. Let f be a function in AB, whatever the oscillation oscillation of f in or at or above or whatever AB is denoted with the letter omega, little omega, which is a W that will stay too long in the sun, or little but, I don't know how you think about omega, is denoted omega and is defined as follows. Omega is the difference between the supremum of F and the infimum of F in our segment. Intuitively, sub F is the maximum and infimum is the minimum. But we know that mathematically there can be a difference. The maximum is a point which we actually have in the segment. One can plug it in and get the value. And supremum is sometimes something that we just tend to, we don't actually get it in the segment itself. So omega is difference between the supremum and the infimum. Now, when we have a partition and the partition has subsegments, we can define the oscillation in every subsegment. When we have a partition P of the segment, we denote the oscillation in the of the in the subsegment between xi minus 1 and xi with omega I omega I omega I is the sum of f minus the infimum of f. When we look at the segment xi minus 1 xi. So the difference between intuitively the maximum value and the minimum value of the function. And one can define it for every subsegment. Now, as I mentioned before, we talked about the Darboux approach for integrals. One can look at the rectangles which are always above the function, and on the other hand, rectangles which are always under the function. And they're getting closer and closer to each other when we add points to the partition and to the point choosing correspondingly. And then if they do touch each other, kiss each other, when the number of points tends to infinity, then the integral is defined. So our proposition will say the same using the language of these oscillations. So let's write it down. It can be a theorem if you want, but I'm not going to prove it. In our time left, I'm going to explain why is it true, but not going to prove it. Don't have time for that. Theorem. Let F be a bounded function in A and B. Then F is integrable if and only if for every sequence of partitions Pn with parameter lambda goes to 0, when m tends to infinity, we have the sum of omega I multiplied by delta xi goes to 0, tends to 0. Instead of using the limit in a definition, which needs two sequences, one of partition, one of point choosings, we can use only one sequence of partition. Yet again, every partition is a set of elements with more and more elements as m tends to infinity. It's a complicated definition comparing to the definition of a derivative. And there are probably very much complicated definitions in mathematics generally. Now, it is somehow, it somehow makes sense, but it's not extremely obvious. I want to, we have like 10 last minutes. I want to explain why it's true, but not, as I mentioned, prove it very rigorously, very mathematically. We have two sides to this theorem. See if you don't leave. Yeah. Um, explain with explanation, another proof. Explanation. If f is integrable, then every Riemann, or שזה Riemann הפוך, I and then E. Oh, where is it? Yeah, you'll understand. Then every Riemann sum has the same limit. Oh, Riemann sums go to the same limit, which is denoted with the integral. Or specifically, that's not right. No.
There's an extra something somewhere. I think it's on the second bit, but
Another E? Would you help it?
no, second bit.
Just two L's?
Yeah.
But
Yeah.
I and E are the same? Okay. Yes.
It's basically the same relation between seconds, time, and second flow. That's without limits, right?
The limit is eventually the area between the graph and the axis. Specifically, we can say that the two sums with one with the sub of f and the second one with the inf of f, let's write the inf down as well, and one can add the sub of inf of f in the specific subsegment that determines one xi. Goes to the same limit. Therefore, if they go to the same limit, the difference goes to 0. Integral minus integral, which is 0. And we get this little fella goes to zero, but one can write it down in just one signature. The sigma of sub minus inf, and sub minus inf is actually omega. So if every Riemann sum goes to the same limit, which is the definition, the very definition of Riemann integral function, then the sum with these omegas goes to zero. This is one direction in our if and only if proof. Why it is only an explanation and not an actual proof of this direction? As you mentioned before, the sub and the inf function are not always actual values of the function. There isn't always a point Ci in which FCI is supernorm of F or infimum of F. We can get closer as much as we want to the supernorm and the infimum without mentioning the actual definitions with epsilon, etc., etc. But saying that there are points Ci which we plug in F and we get sup and infimum is not mathematically, or at least always, correct. In order to prove this direction, not just explain it, one has to overcome this gap. How do we mathematically connect between FCI on one hand and sup in inf of F on the other hand? Hey, come, pizza. No. Third week of the semester. Where are you going? So just an explanation. But the intuition is good. I'm not planning on proving it correctly in the next lecture. We have a lot of different things to do. But I planned on plan on explaining. So this is one direction. Intuitively, why is true? For the second direction, on the other hand, if this little fella goes to zero, then, as we already seen in the first direction, the sup and the inf tends to the same limit. Let's call it L, because you know limits. Something similar to what we're reading out here. So omega is the difference between sup and inf, and if sup and inf, difference between them goes to zero, it means that sup and inf goes to the same limit. So your difference will be zero, right? So f of Ci is always between the infimum and the supremum, whatever it is called. Means that the equivalent corresponding sums acting the same, the sum with inf and the sum with sup bounding the sum with FCI. Where are you? Control CU, then control CU. By the sandwich rule, if sum of int and sum of sub goes to the same limit, then sum of FCI goes to this limit as well. For every PM, for every CM, etc., etc. Using the sandwich. That's me, right?
Yeah.
We still get age?
That's fine.
Okay. Sandwich rule. We get that every sum FCI sigma I goes to the same limit, meaning f is integrable. And why is it? Just an explanation, not a proof, and we finish here. Saying that if the difference goes to 0, then each of the components of the elements of the difference goes to the same limit is not true.
It has to go to 0 for this to happen, or
No. If, let's more simple, let's say it when in sequences. If two sequences goes to the same limit, the difference goes to 0. Correct. But if the difference goes to 0, it doesn't mean that every sequence goes to the same limit. Maybe the sequences are not even convergent. For example, let's take -1 to the power of n, -1 to the power of n. The difference is 0. And so it goes to 0. But every sequence itself is even convergent. It's divergent. So saying the difference goes to zeros, everyone goes to the same limit is not completely true. This is the gap one should overcome if he wants to have a complete proof and not just an explanation. But we already finished. An explanation is totally fine for me.
fine. If we
Any questions, dear friends?
no.
So, next lecture, B'ezrat Hashem, we're going to state, probably prove, that every continuous function is integral